we have Miguel Montero from Harvard, and he's talking about new string theories from discrete theta angles.
All right, thanks a lot, Ana Maria. Thanks a lot to the organizers for putting together this very nice workshop. It's always super nice to go back to Madrid. And thanks to all of you for being here. So I'm going to tell you about some recent work that I've done in collaboration with Héctor Parra de Freitas, and I really want to highlight what he's done because it really is amazing. So this work is about the embedding in string theory of some new quantum theories of gravity in high dimensions with high supersymmetry that Héctor actually predicted on his own in a solo paper he had, using some bottom-up algorithm of classification of singularities on K3. It's really very good work. And Héctor is applying for postdocs this year, which I think is good news for anybody who's looking for a competent postdoc. So what is the big picture here? So I actually think I am the first person, I think in the conference to put the typical Swampland plot. I guess it's obvious for now, but I put it for a reason. So usually, what is the big picture that we try to address here? Usually you think of the Swampland as the set of effective field theories that can be complete to quantum gravity. But you could also ask the converse question. Are there any effective field theories, okay? Given an effective field theory can be embedded in quantum gravity, can it have more than one embedding? Can there be two quantum gravities that are different, but lead to the same effective field theory at low energies? And if you think about it, this is actually also a Swampland question, because if the two quantum gravities are different and they have the same low energy limit, that means that you can distinguish them at some perhaps relatively high intermediate scale at the level of massive states. You can probably distinguish them at the level of massive states, high relative terms, and perhaps topological couplings, things that are trivial in the IR, but which are non-trivial in the UV. Okay, so the question of understanding possible UV completions of an effective field theory is also a Swampland question, but it's a difficult one to answer. I mean, it's hard enough to understand the Swampland of low energy effective field theory. So this kind of question is more naturally asked in those corners of the landscape where we actually understand the effective field theories that can arise pretty well. And that's, for instance, the case of theories in high dimensions with 16 supercharges, okay? There's a lot of supersymmetry, a lot of Swampland conditions, and we believe we more or less understand the set of effective theories that can arise. So we were thinking about this in this arena, and with Héctor's techniques and by thinking about the string embedding, we were able to find 3 new examples, 3 string compactifications, 3 new quantum gravities in 7, 8, and 9 dimensions that we had missed. And you know, the classification of this actually, it's interesting because they're the first examples like this in a long time. And what is the technique that we use? What is how do we construct these guys in string theory? The thing that all 3 examples have in common is that we are able to get them from known examples by introducing what we call what is called discrete theta angles. What is a discrete theta angle? It's like your theta angle that you can find the QCD Lagrangian. But rather than involving U1 fields or continuous fields, they involve discrete fields. And that means that they're difficult to see in the IR. You don't see them in the low energy effective field theory, but they can change the theory and you will see they change the spectrum of massive states in a kind of drastic way. So without any further ado, I've been telling you how this is amazing. You will see now how actually the basic idea behind it is very stupid, really, it's very simple. So let me give you the first example. I'm just gonna flat out give you the new string theory that we found. To do that, we need to go to type 2B in 10 dimensions, okay? So type 2B string theory has many symmetries, and in particular, it has 2 different perturbative Z2 symmetries, which we call omega, which might be familiar from you use it to construct oriented folds, and -1 to the FL, worksheet left moving Febner number. And these 2 guys are dual, S-dual to each other, okay? And one thing that both of them have in common is that on the Ramon-Ramon action C0, they both act by flipping the sign, okay? So there's one string compactification, which was constructed in 2004 by Hellerman, which is the following. It's a very simple idea. Take type 2B, put it on a circle, and put a Wilson line for either omega or -1 to the FL, okay? that projects out a number of fields, in particular the Ramon action you set to 0. And you can show that the resulting theory has 16 supercharges, okay? So you end up with a theory with 16 supercharges. It's one component of the moduli space of theories with 16 supercharges in 9 dimensions. If you do omega, it's called the double car park. If you do -1 to the FL for the Wilson line, it's S dual description. They are the same theory, different values of the coupling, which is called the asymmetric orbital of type 2B or A of B background. It's just one thing that you can do. And with 16 supercharges, things are very simple. You just have the gravity multiplet and vector multiplets. So basically, the only one label we use to label the theories is the number of vector multiplets, which is the rank. So what you have constructed here in very simple ways is one of the actually 2 known components of the moduli space of quantum gravities in 9 dimensions, which have 1 vector multiplet, the moduli space of rank 1. So there's two disconnected components. This is one of those. Okay, so that's the old story. What did we do? Well, Ramon action is periodic, right? It's only defined up to shifts, which we take to be 1. And if you're putting it if you're putting type to be on a Wilson line on a circle with a Wilson line for omega r -1 to the FL, you flip the action, and because it's periodic, there's actually another solution different from C0 equals 0. You can also set C0 equals to 1/2. And so this is what we did. And I will give you evidence later that this thing actually is a new string theory, lives on a new third component of the moduli space, and it has a new property, which is not seen in any other component of moduli space, which is that the spectrum of BPS strings is not complete. I will explain that. But the basic idea you see is extremely simple. In fact, you could say it's too simple. You could ask, okay, why hasn't this been done before? If this idea is, I mean, this is really very stupid. Why hasn't this been tried before? I'm sure that people have thought about this, but the problem is that in the previous discussions of the literature of this kind of idea were extremely confusing. They seem to lead to nonsense. So if you don't understand the one example, then you're wary of studying others. So what do I mean that previous discussions led to confusion, to nonsense? Well, what I'm telling you basically is that wherever you flip the Ramon action, C0 goes to -Z0, that equation has 2 solutions. And another setup in which you do the same thing is type 1 string theory. How do you construct type 1 string theory? You do a O9 orientable of type 2B, and the orientable also projects out the Ramon action. So you could do the same thing. And in fact, there's a beautiful paper by Sapseti in 2013 where he proposes, let's just do that. And so I get Z0 equals to 1/2, and I get a new string theory in 10 dimensions, which some of us call the Seti string. And so it seems a thing like a thing that you can do, but then it gets very confusing. You just do try to start tracking this theory throughout the duality wave. And for instance, when you put on a circle, it seems it's dual Duhem theory and a Mobius strip, which has the wrong rank. There's several paradoxes. So on one hand, it's an extremely nice, natural, reasonable thing to do. But on the other hand, if you just think it's a different theory, try to follow through dualities, you get nonsense. So when you get something like this, you're just confused, and you typically work on something else, because it's like, sure, it seems nice, but there's clearly something we're not understanding. And there's several possibilities here. Could be that dualities work differently for this theory. It could be that it's illegal to say C0 equals to 1/2 in this example for some reason, perhaps some anomaly or something. And so if you want to understand discrete angles in string theory, really the first thing you need to do is to figure out what happens in this example. And so that's what we did. And when I say we did, actually what we mean is we read the literature, and actually the solution is written in a paper of Witten from 1998, but it's just it's an offhand remark in a paragraph, which is essentially that the Seti string actually turns out to be completely equivalent to ordinary type 1 string theory. And why is that? Well, it's an argument by Witten, and then when we were going to publish the paper, we learned that that Bergman gave a seminar in Oviedo in 2015, which never became a paper, in which basically essentially outlines the same ideas. The idea is very simple. It's something that is familiar from other effective field theories. It turns out that type 1 string theory has fermions, massless fermions. And if you just look at the type 1 Lagrangian, they seem to transform in a vector in the general representation of O32. Now we always say the gauge group of type 1 string theory is SO32, not O32, and that's because the type 1, this is something which has been understood for 20 years or more. The disconnected part of the gauge group here is anomalous. Okay, there's an anomaly in this transformation, so it's not actually a gauge symmetry, and the honest gauge symmetry, which is the exact symmetry of the theory, is just the SO part. So why is there an anomaly? Well, what that means is that when you act with an O32 transformation, the fermions pick up a minus sign. And what you can actually see, and I'm skipping the details, is that acting with this transformation, which introduces a minus sign in the determinant of the fermions, you can explicitly see on the Lagrangian level that is equivalent to changing this discrete theta angle. Okay? So the anomaly can also be recast as saying that C0 equals 0 and C0 equals 1/2 are a choice. They are related by a case transformation. And the phenomenon that I'm describing here is literally the same thing that happens, for instance, in QCD when you have massless quarks. If you have massless quarks, you have a continuous theta angle. And just by doing a chiral rotation of the quarks, which is an anomalous symmetry, the meaning of the anomaly is that you can shift away the theta angle. So the same thing happens here. And so the theta angle actually becomes unphysical. And we actually check this is consistent with duality, and we used it to learn some features of the physics of deep branes hitting O planes and stuff. But the bottom line here is that we understood what was happening with this theta angle in the set string. It's just really not there for a very concrete reason that you can see in the effectivity theory. There is an anomaly in the discrete theta angle. There's an anomaly in the fermions which can shift the discrete theta angle. So once you understand it here, that means you can understand it. That means you also, in principle, understand it in other setups. So going back to the double card background, which or the AOB, which is, I remind you, type 2B compactified on a circle with a Wilson line. It turns out that in this theory, there are no fermions which can have the anomaly that can shift this theta angle. Okay. So that means, in principle, in these cases, the theta angle can be physical. So they can be, but that doesn't mean that they are. How can you actually see if the theory with the theta angle turn on or off is the same theory as a different one? And you need to look at the spectrum of excited states. And in this case, we're able to see in a very clear way that the two theories are different, and they differ in their spectrum of strings. Okay. The particle spectrum is the same. Even the spectrum of massive states is the same. But the spectrum of the strings themselves is different. So why am I talking about strings? All the theories with 16 supercharges, they have a two-form in the part of the gravity multiplet. So it's a two-form field. And by the completeness principle, you expect there's strings which are charged under it. Okay. And in different theories with 16 supercharges, the strings will have different microscopic origin, because the B field itself that forms part of the gravity multiplet will have a different origin. So for instance, for the AOB or double card backgrounds, the action of the orientifold projects out either the Ramon 2 form of type 2B or the Navier-Stokes 2 form. And so you're left with the one that remains. In particular, for instance, if you take the AOB background, which is a Wilson line from -1 to the FL, you're left with the Navier-Stokes 2 form. So to show you that the two theories are different, I'm going to focus on this perspective, on the AOB perspective. So what I'm going to do is take the AOB background so that the two-form field that survives at low energies is just the Navier-Stokes 2 form of string theory. And of course, that means that the fundamental strings in this theory, the strings that couple to the gravity multiplet, are just the fundamental strings of type 2B. Just put it on a circle, you haven't projected out this field, so the strings are still there. So let's first analyze the theory without the theta angle. So without the theta angle, what I'm drawing here, let's see if I can. Okay. Okay, so what you see here, I've been drawing. So what we're taking here, we're putting a Z2 Wilson line on a circle. I can draw that in terms of the covering space, okay, where I put the same circle twice, and I just look at states which are invariant of the action of the Wilson line I'm putting. So for instance, if I want to introduce the state of smallest string charge in the covering circle, I need to put 2 copies of a fundamental string, okay? And with z0 equals 0, this is the guy that generates the charge lattice. Everything is nice, simple, and beautiful. There's no problem with it. Okay. Now, what happens when I set the new component, z0 equals to 1/2? Well, this guy is still there, and the monotomy now I introduce a T generator. The T generator, I mean the T of SL to Z duality. That's the guy which shifts z0 to z0 to z0 plus 1. So this is just a way of encoding that we're in the component with z0 equals to 1/2, and this guy is still there. There's no change, but now I can also do this. Instead of starting with a fundamental string, I can start with a D1 brain, and because I've turned on the Ramon-Ramon action, and the Ramon-Ramon action shifts the lattice of PQ strings, acts kind of like a Witten effect. When I look at what's the image under this transformation under the monotomy, it no longer goes back to it's no longer the same brain as I had before. It happens here, but it's SL2C transform, and the SL2C transform happens to be a 1,1 brain in such a way that if you count, so the charge under the never source field here is the total charge of the 2 things on the first component of these vectors. So here you have 0 plus 1, 1, which is to be compared with 1 plus 1, 2. Furthermore, these 2 branes here are BPS, and that means that the state I'm describing there is BPS. But these 2 branes are not BPS. So the string of smallest charge in this theory is very explicitly a non-BPS string. Okay. This is unlike any example of theory with 16 supercharges that we knew before. And in fact, I would say that if you think about this from Swampland point of view, this is really the interesting feature that these theories have. They are the first examples where you violate BPS completeness for strings. Okay. What is BPS completeness? It's the idea that for every value of the charge, you have a BPS represented. Okay. In this case, the string of charge 1 is BPS. It's not BPS, but for even charges, it is. So we already knew examples, and so Dean was just talking about the sublattice regarding conjecture for particles. That's precisely what that is in the BPS context. Is sometimes with particles, you just don't have a BPS state of charge 1 or 2, but you have a state of charge 3. I didn't know an example involving strings, and certainly not involving strings with 16 supercharges. And so that's interesting, but it's more than a curiosity because there's been many Swampland papers using these beautiful techniques using anomaly inflow to constrain quantum gravity. So the idea is if you have a BPS string of charge 1, for instance, then by looking, the effective field theory of this string is very much constrained by anomaly inflow and by the fact that it's BPS. And so you can use it to put very strong constraints. You can even put some theories in the Swampland. Like for instance, I think you can, for instance, in 6 dimensions, there's a family of theories which have they cancel local anomalies. Have like n copies of an E8 gauge group. You can put in the Swampland with these techniques. And the basic idea there was that, well, since in every example we have a full spectrum of BPS strings, it's a reasonable thing to imagine that maybe this is something that happens generally. Now we know it doesn't. So if you use anomaly inflow to put constraints on strings in 6 dimensions or in 10 dimensions, you should take this with a grain of salt. It's really a constraint assuming that there's a BPS string of charge 1. The one thing you can do is you repeat the constraint, assuming that the string has charge n, and see for which n you get a constraint, for which ones you don't. And of course, in this talk, I'm only going to give you examples where the sublattice of BPS strings is 2 or 3. So again, we only find small indices, but conceptually, I think it's an important point. So we actually completely understood the moduli space of this theory has many dual descriptions. So this is a very nice figure that we reproduced from the Heinrich and Margotsky Patir paper, where they summarize the moduli space of this theory. They have the theory has the double part background has duality group SL2C, and there's different phases where it's described with the AOB background, double part, and some compactification involving orientifolds. And what we have is a version. We found discrete theta angles in all the components which exactly match the descriptions. And you can see that the moduli spaces, they look the same, but they're not quite the same. And that's because the duality group is a bit different. Because of the theta angle, the duality group actually is a subgroup of the modular group. It's a congruent subgroup, which fits very nicely with a swampland conjecture a couple of years ago by Jonathan Heckman and Marcus Dier-Eagle. They were putting a constraint on which duality groups you could have in theories with existing supercharges, and this was one of the groups that they were saying was allowed. So that's also interesting. They actually made a prediction there, which was verified. Okay, so we fully understand the theory in 9 dimensions now. This is a 9-dimensional theory. One thing that we can do is keep going. Let's compactify. Sometimes in string theory, when you compactify, sometimes you get a nicer, easier description of stuff. And this is the case here. If we compactify the theory on a circle, we get an 8-dimensional theory, which has and when we were able to see that it has a corner of its moduli space, what is described by a completely smooth geometric M-theory background. It's just the non-trivial vibration of the Klein bottle over a circle. Okay? When you put it like that, it's extremely stupid. It's just very simple. It's just here's a geometry that people have not looked at. People have looked at the other component of moduli space. So the other two components in 9 dimensions. When you go to 8 dimensions, they become different corners of the same moduli space. And that moduli space can be described as Klein bottle times a circle. So the trivial vibration of Klein bottle over a circle. Okay? So why did people miss this theory from the 8-dimensional point of view? The way I see it is just because people have not systematically studied the kind of backgrounds with 16 supercharges that can give you a supersymmetric background in M theory. In particular, this one is non-orientable, so it's a bit weird. But in the end, it's a regular M theory compactification. So once you discover this description, I'm telling you, like the way we figured this out historically. We started with the AOB background, and then we were like, well, this is very geometric. I mean, if people miss this, are we missing more compactifications like this? What is the way to classify geometric compactification, geometric backgrounds with 16 supercharges? Well, this is a question that we all are familiar with the answer. Actually, in the more complicated cases with less supersymmetry, when you have 8 supercharges or 4 supercharges, you look at G2 manifolds, K3, Calabi-Yau manifolds, so they are Ricci flat. The basic thing that comes out of the supersymmetry variations is the metric is Ricci flat. And when you have 16 supercharges, it's actually, as you would expect, is stronger condition, easier in a sense condition. And the condition you get is that the metric has to be a Riemann flat. Okay? So locally, on an open patch of any point, it really looks like Euclidean space. So that's a space which is extremely constrained. There can be no curvature, there can be no sectional curvature. It's very boring. In fact, it's so boring that these manifolds, the analog of the Calabi-Yau condition, have been completely classified. And they are quotients of tori by a certain kind of groups, crystallographic groups that act freely on the tori. But it's just a quotient of tori by a free action. And these manifolds, because they were classified by Bieberbach, they're often called Bieberbach manifolds. And for low n, and by low n I mean all the n's that are n equals 2, 3, 4, they are classified in the math literature. And for 5, 6, we know how to do this. It just hasn't been done. It requires like some you can do it with crystallographic programs. But for low n, they've been classified in the math literature. So if we're interested in 8-dimensional theories, let's just look at the 3-dimensional Bieberbach manifolds. What happens when you compactify M theory on 3-dimensional Bieberbach manifolds? They've been classified. They are called, in some paper that we found has a nice classification, they are called like this. This just means this like orientable torus vibration. So they can always be written. I write it like that because what you have here is really a mapping torus for this T2. And as you go around the S1, you pick an SL2C monodromy by this element, or GL2C in general. And notice that there's 2 examples here, which actually correspond to the two things I was describing, the trivial and non-trivial vibration of Klein bottle over a circle. Now, so these are the 2 theories that we found, and we actually checked, because the thing that you need to check on top of one of these manifolds is that you have actually a covariantly constant spinner. That doesn't always happen. And in this table, it only happens in these two examples. So from M theory point of view, this is all there is. In principle, we found all there is from everything that has a smooth geometric M theory compactification. These guys just don't admit quadratic constant spinors. Does that mean that these guys are boring? Well, no. They just have a different use. The fact that they are quotients by an SL2C element means that even though they do not admit quadratic constant spinors, they admit quadratic constant SL2C spinors. Meaning, if you act with an SL2C transformation, you can actually construct quadratic constant twist spinors. And which theory do we have that has an SL2C symmetry? Well, that's type 2B. So what you can use these guys, you cannot use them to produce new theories in 8 dimensions, but you can compactify type 2B on them to produce new theories in 7 dimensions. Okay, so you actually, this way you discover, you discover a new description in completely smooth supergravity description of some of the low rank corners of string theories that we know with 16 supercharges. And the nice thing of doing it like this in a completely smooth supergravity way is that now it's apparent that 2 of these components actually admit new discrete theta angles. So you can turn them on, and just as before, these discrete theta angles now they're in both periods of C2 and B2. Never mind that. You can just put them here. And as you get them, so you get for n equals 3, you get a discrete C3 theta angle, and for n equals 4, you get a discrete C2 theta angle. Okay. And in both cases, again, turning on the theta angle means there is an incomplete PPS spectrum. Okay. So it's the same story again. So this is just a picture of how the landscape of theories with 16 supercharges looks like now. We have the theory, its dimension and its rank. So we have all these guys that we described, all the guys that come from periodic with fluxes, and those 2 examples with discrete theta angles. Okay. Now, this is a talk in a swampland workshop, and just to finish, I have just talked about enlarging the landscape. Didn't talk about the swampland. Didn't put any swampland constraints. There were no conjectures here. So in the last 2 minutes, I'm going to remedy that. And I will describe what could be a conjecture based on the new results that we found. But still something I'm thinking about, and it might just be wrong. You might actually, off the top of your head, come up with a counterexample. If so, let me know. So the interesting observation here is that we have a lot of components of moduli space in higher dimensions, but there's something very fun about it. Until we did our work, some of these components didn't have a geometric description. So for instance, there were some components of moduli space which you could only describe as K3 with some process singularities. But for instance, this one, we can now describe as type 2B on this Bieberbach manifold. It's completely smooth supergravity description. And because we included these new components, now everything that I know has a geometric description. And this leads me to perhaps imagine that it is true that if you have quantum zero gravity with a Minkowski model, which is supersymmetric and has Minkowski vacuum, every component of the moduli space has a corner which is captured by supergravity on a smooth manifold. I really mean no brains, no orientifolds, just compactify supergravity on a smooth manifold with bundles. If this is true, it would be awesome because it means that just by studying smooth supergravity compactification on smooth manifolds and then following Liam's, for instance, techniques or some other techniques to explore corners of moduli space, you will really get every quantum gravity. And in a sense, supergravity has a peek at everything. That's what this means. So what's the evidence for this? Explicitly true for every case that we know in more than 7 dimensions. This is funny. If Reed's fantasy is true, I can always connect everything in Calabi-Yau-like moduli spaces to a smooth Calabi-Yau. So it's also true there if this is true. And for 4D equals 1, you typically don't have a moduli space, but in the cases where you do have a moduli space that we understand, that actually can be reduced to the previous case. So also true in the example that we have there. And it's interesting, this is a conjecture which becomes more non-trivial the more supersymmetries you have, because with low supersymmetries, you would think we just have one part of moduli space. So the questions, obvious questions, is this true? If it's true, is there any reason? If there's no reason for it, perhaps it's not so interesting. How to generalize? what are the applications or consequences of it? But just to recap, we found 3 new string theories by thinking about discrete theta angles from some perspective. They are models which are very relevant for the SWAMP because they don't have a full lattice of BPS strings. And I think this biback approach, if followed systematically, can uncover even more theories with system supercharged in low dimensions. That's it. Thanks very much.
Questions? Sorry, I don't see very well. There are 2 questions, 3 questions back there.
Thanks, Miguel. Sorry, losing my voice. Is it also possible if you compactify on a Bieberbach manifold which breaks supersymmetry?
Absolutely.
That but that actually you have also a supersymmetric lower dimensional theory with a vacuum that explicitly breaks supersymmetry. Say some gauge supergravity with a Minkowski vacuum.
So you can definitely do this. You compactify in non-supersymmetric manifolds, and you're going to get a lot more quantum rays. There are going to be examples of non-supersymmetric string theories. Yeah, that's completely fine. You can actually stay. That's completely right. Yeah, Ana Maria, they just looked at it and they found something very interesting. They found that, correct me if I'm wrong, Ana Maria, you find because they also studied not just in supergravity, also in the worship, they find tachyon. It's very interesting. Whenever there's no supersymmetry, they find a tachyon at small volume. It's really a lot of fun.
Hi, Miguel. Nice talk. So I had a question about the implications for the conjectures that use the BPS completeness. So do you know any cases where you can definitely say that some of those results are changed? Because I mean, it sort of seems like what's happening here is really that you have new strings of charge 1/2.
Yeah.
And I wonder whether the arguments kind of just go through as before.
This I haven't thought about. This absolutely haven't thought about. So the only thing I did is make the point of principle. But definitely the charge of the string enters this kind of arguments. Okay, so for instance, when you do inflow on a worksheet of charge q, the inflow is q times the inflow of the thing of charge 1. Okay, so if the string has charge 2, that means that you get twice as much central charge that you have with charge 1. I understand what you're saying. You're saying fine, but the same string is still there in the spectrum. Yeah, that's a good point.
Yeah, can you explain a little better what you mean by SL2C covariant spinors?
Yes, so I just mean, okay, so if you think about the spinors that you have in type 2B, let's say there's 2 dilatini or 2 supercharges, right? And they transform in SL2C. So one thing I can do, suppose I compactify on, on a circle, and what I can do is if I put an SL2C Wilson line on the circle, what that means is that the equations of motion of the spinor satisfy, okay? They are transforming to each other with an SL2C transformation, okay? And sometimes that equation can have constant solutions, covariantly constant spinors, even when the ordinary equation, which is not twisted by SL2C, doesn't. That's what I mean.
But then the manifold is still geometric.
The manifold is absolutely geometric. You're just putting a bundle for some internal symmetry of the theory. In this case, SL2C. It's the same manifold. It's like spin C. Like when you have U1 fields, sometimes you can have, spinors which are flat involving, because they also charge under a U1 connection, and that makes them flat, even though the manifold is the same.
Okay, I'm afraid we have to go to the picture session. So let's thank Miguel again.